Hello, I am Faizan Shakil, but I am going to present on this research topic named RetinaFace, single-stage dense face localization in the wild. The paper I selected for my assignment is purely based on the image processing, in which the main focus is on face detection in the wild, where input and output is the image. The model used in this research paper was RCNN, region-based convolutional neural network, which is a deep learning approach, helps to select the particular region instead of working on the entire region. Also, we will talk about the dense regression loss and multitask loss in this presentation. So, what I am covering in this presentation is the introduction, the related work to this topic, the retina phrase in the brief, some experimentation done in this paper, and the conclusion with some references, and at last I will present the code implementation through Colab. So what is the problem statement? Face detection in the wild always remained a challenging task. Detecting a single face is easy, but detecting the multiple faces simultaneously with high efficiency always remained a challenging task. So, this paper proposed a solution for face detection in the wild with high accuracy rate. The plus point of this module is that it is a lightweight. Here you can see in this image, this is the world's largest selfie containing 1153 faces, out of which 900 faces were detected by the RetinaFace with a threshold of 0.5. Face detection. We can say face detection is an AI-based technology to detect the human face, or in broader sense, we can say locating the face, detecting the face landmarks, which in this paper is 5, like 2 eyes, centers, nose tips, 2 mouth edges. So, how the processing is done? First, it is locating the face. It's locating the face, then locating the landmarks, which is shown in yellow dots. We also call these annotables in this paper. After this, we are getting the region of interest in which we are interested. After that, then registering the face with the certain pixel size. RetinaFace. In RetinaFace, the proposed single-stage pixel-wise localization method employs the extra-supervised and self-supervised multitask learning in parallel with the existing box classification and regression branch. First, we are doing the face classification, which is given by the LCS, and then localizing the face, which is given by this function. Then for extra supervision, we are checking for the facial landmarks, then for the dense face localization. The main contributions of this paper are the following. This paper proposed the robust single-stage face detector named RetinaFace, which employs a multitask learning strategies to simultaneously predict face score, face box, 5 facial landmarks in 3D position, and correspondence of each facial pixel. Manually annotate the 5 facial landmarks on the wide face hard dataset, which improved the hard face detection. Here in this paper, by employing the lightweight backbone network, RetinaFace can run on real time on a single CPU for a VGA-resolution image. RetinaFace outperforms the average precision by 1.1% of the state-of-art two-stage method on wider face test set. Also, on the IJB-C dataset, RetinaFace helps to improve the ArcFace verification accuracy, as it increases the efficiency of the hard face detection on the wider face hard dataset by annotables. So let's talk about some related work to this research. Image pyramid and a feature pyramid. As in this paper, we have used the feature pyramid, but the image pyramid were earlier used in some research papers. But the main thing in the image pyramid was the cascade chain to reject the false face regions in the image pyramid. But with the emergence of the feature pyramids and sliding anchor on multi-scale map quickly dominated the face detection. Image pyramids was actually time consuming and requires the high memory requirement. Normally, we used to work with an image of constant size, but in some occasions, we need to work with images of different resolutions of same image. Example, while searching for something in image like face, we are not sure of what size the object will be present, at what size the object will be present. So this is the high resolution image, and then this is half of that resolution. Then we're decreasing this to 1 by 16th. So two stage and single stage. Our research is based on the single stage phase detector. So we propose the single stage phase detector, but there is also a two stage which use the single scale input image and a single scale features map to learn multiple scale features. Two stage method focus highly on localization accuracy, while single stage method densely sample face location scales. Compared to two-stage methods, single-stage methods are more efficient and have high recall rate, but at risk of achieving the false positive rate and compromising the localization accuracy. So to handle this imbalance, reweighting is done in this context. So context modeling. Uh, Context modeling is just to enhance the reasoning power of the module. RetinaFace is based on the feature pyramid with independent context modules. In the end, it is the small image. The head level is selected from the first layer. Here we go a little bit deeper to pull out the features. Nowadays, it's used a lot because of its lower weight and so talking about the losses, we mainly discuss about the multitask loss and regression loss. So multitask loss. So in this, we are doing first the face classification, which is calculated by this function. For box regression loss, ground truth box associated with the positive anchors, we used to normalize the box regression loss target. Here, pi and pi star. Pi is the predicted probability of an anchor I, and pi star is 1 for positive anchor and 0 for the negative anchor. Here the box regression loss is denoted by L box, and the facial landmark regression is denoted by LPTS. So here what Ti and Ts star denotes represent the coordinate of the predicted box, and represents Ti star represents the coordinate of the ground truth box of the positive anchor. So the multitask loss is given by the function as you see L is equal to classification loss plus box regression loss plus landmark facial landmark loss plus pixel pairing. Here, lambda are the balancing, lambda 1, lambda 2, and lambda 3 are the balancing parameters whose value range from whose value for lambda 1 is 0.25, lambda 2 is 0.1, and lambda 3 is 0.01. As here you can see, the L and Li star uh, is the are the parameters for the five facial landmarks, like XY, X1, and Y1 is the the location of the first facial landmark. And actually we're having the five facial landmarks in this paper. In this actually we're having the five facial landmarks that we're using on an image. Dense resolution loss. Once we get the rendered 2D face, we compare the pixel-wise difference of the rendered and original 2D face. Here W and H denotes the width and height of the anchor, and camera parameters and illumination parameters, which are the camera location, camera pose, and focal length. For illumination parameters, it's the location of the point of light source, color value, and color of ambient light. So now experimentation. The dataset used for this research is wide face hard dataset. Wide face is actually having three categories of data: soft, hard, and medium. The dataset consists of 32,203 images and with 3,93,703 face bounding boxes with a high degree of variability in scale, pose, and expression. The dataset is split into training 40% and for validation 10%, and for testing it's 50% by randomly sampling the 61 scene categories. Extra annotations. Extra annotations are the five landmarks which we used in this paper. Extra notations of five landmarks on the face that can be annotated from the wide face training and validation set, which includes 84,600 face on the training set and 18,500 face on the validation set. Here in this table, when the criterion is indisputable, there is no much of efforts in finding the landmarks on faces. Whereas in annotable category, finding the approximate location of landmarks requires some efforts. So now implementation details. RetinaFace employs the feature pyramid levels from P2 to P6. Here P6 is calculating through a 3x3 convolutional network with the steroid equal to 2 on C5. This paper has applied the independent contextual model on 5 feature pyramid levels to increase the rigid context modeling power. This paper also replaces all three convolutional layers with the lateral connection and the context module by deformable convolutional neural network, which strengthens the non-grid context modeling capacity. So there are around 20% of tiny faces in the wide face training set. So we follow the random crops. We also augment the training data by a random horizontal flip and photometric color distortion. About the training details, RetinaFace is trained using SGD optimizer. The momentum at 0.9 and a weight decay at 0.0005 with a batch size of 8x4 on 4 NVIDIA Tesla the 24 GB GPUs. The learning rate starts from 10 raised to minus 3 raising to 10 raised to minus 2 after 5 epochs, then divided by 10 at 55 and 68 epochs. terminating at 80 epochs. Testing details. For testing on wider dataset, it employs flip as well as multi-scale strategies. Box voting is applied on the union set of predicted face boxes using an threshold at 0.4. So, some ablation study. Adding branch of 5 facial landmark regression significantly improves the face box average precision and mean average precision on hard dataset, thus suggesting the landmark localization is crucial for improving the accuracy of the face detection. Here you can see in this table feature pyramid plus context on easy, medium, and hard dataset, giving these values with a mean average precision. On adding the deformable convolutional neural network, the values are changed. After adding the 5 facial landmarks, regression significantly improves the face box average precision and mean average precision on hard dataset. So these are the face box accuracy validation curves. So you can see from the list that RetinaFace outperforms the other models. This graph is for the easy validation set, as the wide face dataset is having 3 categories: easy, hard, and medium. So this graph belongs to the easy wider face hard dataset for validation, which Retina outperforms with 0.969%, and on medium, RetinaFace outperforms by 0.961. And this graph is for the hard validation set, where the RetinaFace value comes out to be 0.918, following the ISRN and SRN and FAN and DFS models and FastNet. These are for the face box accuracy for the test data, where RetinaFace also outperforms with a 0.96 followed by the ISRN, and for same for the medium wider face dataset. And for the hard test dataset, RetinaFace comes out to be 0.914 followed by the ISRN. For the 5 facial landmark accuracy, to evaluate the accuracy of 5 facial landmark localization, we compare the RetinaFace with MTCN on the AFL dataset with 24,386 faces, as well as the wider face validation set with 18,500 faces. Compared to the MTCN, RetinaFace significantly decreased the failure rate from 26% to 9.37%. This is the cumulative error distribution curve, where you can see clearly the RetinaFace and the MTCN decrease the failure rate from 26% to 9.37%. Dense face landmark accuracy. We evaluated the accuracy of dense facial landmark localization on AFL 3D dataset corresponding 68 landmarks with 2D coordinates, and all landmarks were 3D coordinates. Here the mean error is still normalized by the bounding box size. In these two CED curves, cumulative error distribution curves, the performance gap exists between the supervised and self-supervised methods, We can see that 5 facial landmark regression can elevate the training difficulties of the dense regression branch and significantly can improve the dense regression results. In this figure, we compare the dense regression result from RetinaFace and the mesh decoder. RetinaFace can easily handle the face with pose variations, but has difficulty to predict the accurate dense correspondence under complex scenarios. As you can see the below picture with the glasses, uh, mm, it has some difficulties to predict the accurate dense correspondence. So this is the upper mesh decoder, and the lower is for the retina phase. Face recognition accuracy verification performance is given by the percentage. So here you can see in this table MTCN plus ArcFace on a CFP dataset gives the accuracy of 98.37%, and RetinaFace plus ArcFace giving the accuracy on CFP FP dataset to 99.49%. This the result on CFP implies that the retina face can boost the accuracy of ArcFace from 98.37% to 99.49%. Inference efficiency. During testing, retina face performs the face localization in single stage, which is flexible and efficient. Beside the heavyweight modules, like you can see the RCNet 152, which is having the size of 459 MB, where our module for mobile FaceNet, which is approximately 1 MB. For these are the three columns where you can see the easy, medium, and hard mean average precision values are given on the wider face data set. For here the star denotes the result reported in the original papers. For the proposed model with the highest validation mean average precision, the mean average precision from validation and test sets are at the left side and the right side of the slash from for easy, medium, and hard column. Conclusion. With the challenging problem of dense localization and alignment phase, the paper proposed a single-stage solution, RetinaFace, which outperforms the state-of-art method. Further, RetinaFace is combined with the state-of-art practice for face recognition. It is obviously improves the accuracy of the module. So at the last, here you can see the retina face as first detecting the face detection, then 5 landmark detection, and which is then extra supervision by face 3D reconstruction, pixel wise construction on the face detection. The average precision value is 91.4%. The ArcFace with retina face increase on the IJB dataset increase its efficiency also. So this is the lightweight backbone real-time interference mobile net. Here are the references. Here are some references for you. You can find the paper link, the main paper link is given there. Also the GitHub link. Also I have implemented the code in the Colab. You can find it under the Google Colab link. If you have any questions, you can write me to the email. There are some readings which I use while reading this research paper. These readings may be helpful for you. So let's go for the implementation. So here is the implementation. I cloned the Git repository RetinaFace. Then I installed some requirements which we used to run this code. So these are downloading some important files from the Git and putting it to the directory RetinaFace. I'm having a bit slower connection, that's why it takes a time. So here comes some these are already there, so they are uninstalling it. So for training it will require a lot of time, so I used a trained model. I downloaded from the Google Drive, so here I'm downloading it from the Google Drive, and I'm running a test image on it, which is this image with 25 faces. So here I am testing this module for this image. This is an example. Here you can see there are like 25 faces approximately. So here we got the results. Here you can see the face are detected with their accuracy with the 5 facial landmarks. You can see these dots: blue, yellow, and green, red. These are the 5 facial landmarks on which the face are detected, which really increases the accuracy of this module. So thank you for watching this presentation. Hope you like it. If you have any questions, you can write me down. Thank you for watching. I hope you understand this presentation, you like the presentation. If there's any questions, you can write me in email, or you can comment down in the comment box. Thank you so much. Bye bye.